And welcome back to Richardson Chemistry, lesson 13.4. Today we're going to look at calorimetry, which is a process that allows us to compare and determine the specific heat of different objects. The image we see here is a calorimetry cup, oftentimes just a styrofoam cup, could be a coffee cup even, as simple as that. We do have specific calorimetry cups, which are very much like a coffee cup, that have a lid on them. A little hole in the top to stick the thermometer down into the water. The reason that we like to use styrofoam cups is because styrofoam is a very good insulator. So it's going to hold most of the heat inside the cup, which means very little heat, if any, hopefully none, theoretically, escapes the cup to the surroundings. And so we're able to find exactly how much energy is transferred from one object to another, more specifically from the object to the water. What we usually do is we should take a piece of metal. This is a hot piece of metal. When I do the lab, I like to use a cold piece of metal, and we place it into the water. And as the water changes temperatures, we're able to calculate the amount of energy that goes into or out of the water. And using that, we can assume, again, because we're using a styrofoam cup, there's no energy lost to the surroundings. So using the amount of energy that is used to change the temperature of the water, we can say, well, that must be the amount of energy that was gained or lost by the piece of metal. So here's the idea. Again, and you guys will do this lab. We'll stick a thermometer into water. We'll find the temperature of the water. Then we'll put our piece of cold metal into the water, and we'll watch the temperature of the water change. Again, we can use that to calculate the amount of energy that was lost by the water. That's the exact amount of energy then that must have been gained by the metal. Where did that energy go? It had to go somewhere, because we're in an insulated cup. It couldn't have escaped to the surroundings. So the energy lost by the water had to have been gained by the metal. Because we know how to calculate Q, the previous lesson, Q is equal to M times C times delta T, the same is true of the metal. The energy lost by the metal is the mass of the metal times specific heat of the metal times the change in temperature of the metal. So we can set these two equations against one another. The mass of the water times the specific heat of the water times the change in temperature of the water is equal to the mass of the metal times specific heat of the metal times the change in temperature of the metal. So they're equal, and then they're also opposite, because one is losing, the other is gaining, and that's why I have the negative symbol there. And so using these two equations against one another, we can solve for, well, any number of variables, but usually we're solving to find the specific heat of the metal. So here's an example of how calorimetry works. Say we take a 41.65 gram sample of metal at 100 degrees Celsius and place it in 125 grams of water at 25 degrees Celsius. The final temperature of the water is 30 degrees Celsius. Determine the specific heat and the density of the metal. So again, what we're doing is we're saying that there's an amount of energy that was gained by the water, and that must be the exact same as the amount of energy lost by the metal. We're in a calorimetry cup. There's no energy lost to the surroundings, so the two energies must be equal. So we can substitute in our equations for Q. Mass of water times specific heat of water times change in temperature of the water will be equal to the opposite of the mass of the metal times specific heat of the metal times the change in temperature of the metal. Again, I like to list out my variables. They told me I had 125 grams of water. I know the specific heat of water, 4.184 joules per gram degree Celsius. And then the change in temperature is 30 degrees. That's your final temperature, TF minus TI. minus your initial temperature, 25 degrees Celsius. So my change in temperature for the water was 5 degrees Celsius. My metal had a mass of 41.65 grams. The specific heat I'm not sure about, but its temperature changed from 30 degrees, that's where it started out. It started out at 100 degrees Celsius and it finished at 30 degrees Celsius. So you have to imagine our calorimetry cup filled with water started at 25 and it ended at 30. We placed a warm piece of metal into the water and its temperature will eventually be the same temperature as that of the water. So if we leave them both in there long enough, the final temperature of both the water and the metal should be 30 degrees. So my final temperature of the metal is the same as the final temperature of the water, 30 degrees Celsius. This one started out, had a TI, an initial T, of 100 degrees Celsius. So my temperature change for my piece of metal was negative 70 degrees Celsius. All right, now I'm looking for the specific heat of my metal. I can set those two equations against each other. I want to divide out the mass of the metal times the change in temperature of the metal. Can plug in all the variables that I have over here. So 125 grams of water times 4.184 joules per gram degree Celsius of water times 5 degrees change for the temperature change of the water, divided by the mass of the metal times the change in temperature of the metal, and all of that will equal my specific heat, which I find to be 0.90 joules per gram degree Celsius. We should probably be looking back at the specific heats from the table in the notes a couple of days ago, and we can find a metal that has a specific heat close to 0.90, and I think our metal is probably aluminum. So here we have our homework for this evening. A lot of calorimetry problems, but they're not all calorimetry problems. It is definitely possible that there is just a simple Q equals M times C times delta T on here as well. So kind of watch. Again, it really helps to list out your variables. Show yourself what you have, show yourself what you're working with, and make it a lot easier to figure out what you need when you're solving for problems.